Welcome to the Mechanics of Solids lecture series. In this series of videos, we're evaluating beam deflections by integration. Specifically, we evaluate the beam deflection by integration of the second order beam differential equation, d squared v by dx squared equals m of x over ei. In this equation, v is the lateral deflection on the beam and m of x is the moment function. Once we've done this, we can evaluate the peak or absolute maximum deflection on the beam and where it occurs. Here's an example. We have a cantilever beam with a uniform load W. We're asked to evaluate an equation for the deflection v of x by integration and then the peak deflection and indicate where it occurs. Notice that this example is a relatively simple example with a simple load pattern on the beam. The integration method is most suited to simple loading without load discontinuities. It's the only method that allows us to evaluate deflection as an equation along the entire length of the beam rather than just at a specific point. However, if we have a complicated load pattern, we have to use other methods. As a result, we tend to use this method for beams with, we tend to solve the problem symbolically so that the solutions represent the solution to a general class of problems. And as such, we will solve this one using the symbolic variables rather than real numbers, but don't let that throw you off. I usually like to start by sketching the deflected shape on the beam. So here we go. It's a cantilever beam. I know that the deflection at the fixed support and the rotation of the fixed support will be 0 because of the fixity. I expect, because of the downward load, that the deflection will increase toward the right end of the beam and look something like this. Okay, this slope should be 0. Our maximum deflection, therefore, we expect will occur at the right end of the beam at x equals L. We don't have to prove that in this case. We can determine that by inspection. The first step in the solution is to evaluate the moment function. We did this before when we were first learning about shear and bending moment diagrams. Okay, the approach, we need to evaluate the reactions at the fixed support. We can do this quite easily now. The vertical reaction is equal to the total applied load, WL. We also have a moment that counterbalances the moment that's going to be provided by that applied load, and it's WL squared over 2. Okay, so the next step is we make a cut in the beam somewhere in the middle, and we'll draw a free body diagram of the beam to the left of the cut. The distance is general distance x. We're evaluating moment as a function of x. We're going to superimpose over that beam the applied load, the W, the reaction, WL, and the moment, reaction moment, WL squared over 2. And then we'll draw the unknown moment, m of x, at the cut. Okay, now summing moments at the cut, I have m of x equals, and I'm going to write the terms in order from the highest order down to the lowest order. So I'm going to start with the distributed load. Distributed load is acting in the same direction. The moment due to this distributed load is acting in the same direction as m of x. So I'm going to negate the sign. It's wx squared over 2. Just taking a little shortcut here. Then I move on to the reaction, WL. It's acting in the opposite direction of the moment. So it's equal plus WL times the distance, x. And then finally, I have the moment at the fixed end minus WL squared over 2. That's my moment function that I'm going to work with. Step 2 is to evaluate the boundary conditions. Okay, the boundary conditions have to be conditions on deflection and rotation if I'm integrating the second order equation. Both of my boundary conditions are going to come from the fixed support. We said that the deflection is equal to 0 and the rotation is equal to 0. I will express that boundary condition for deflection as v of 0 equals 0. Okay? It's very important that you indicate this where the boundary condition applies. The boundary condition applies at the fixed support and I have my coordinate system centered at the fixed support, so that location is x equals 0. If you don't include the location when expressing the boundary conditions, which I see a lot from students, if you don't include the location, the boundary condition is not correct. Okay, the second one, we said the rotation at that location is equal to 0. Rotation is the derivative of deflection, so we would write that boundary condition dv by dx of 0 equals 0. Now we're ready for the third step, which is to integrate. And we'll apply the boundary conditions to determine the constants of integration. So we have the second order equation, EI d squared v by dx squared equals m of x, substituting what we found for m of x, negative wx squared over 2 plus wl times x minus wl squared over 2. Let's flip over to the next slide and we'll integrate that. Oops, I just noticed that I forgot the wl squared there. That's okay, we're ready to go. We'll back integrate and apply the boundary conditions. Integrate once, ei dv by dx equals negative wx cubed over 6, 2 times 3, plus wl x squared over 2 minus wl squared over 2 times x. Okay, that's the first part. Now we can actually apply this boundary condition right now since we have the first derivative. Let's evaluate dv by dx at 0 equals, first term is 0, second term is 0, third term is 0. I forgot to add my constant of integration, so I have the constant of integration, and I'll set the whole thing equals 0. That tells me that C1 is equal to 0. Okay, I'm going to integrate again. EI v of x equals, now integrate these terms once more, negative w x to the fourth over 6 times 4 is 24, plus wl x cubed over 2 times 3 is 6, minus wl squared times x squared over 2 times 2 is 4, plus I have a second constant of integration. Now I can apply the other boundary condition. V of 0 equals, first term is 0, second term is 0, third term is 0, plus C2, the whole thing equals 0. This tells us that C2 equals 0. When we have boundary conditions at x equals 0, the constants of integration generally go away. So these are easy boundary conditions to apply. If the boundary conditions are at the other end, it's a little more challenging, but still very doable. Okay? So now we'll divide the whole thing by EI. So we have v of x equals negative wx to the fourth over 24 EI plus wl x cubed over 6 EI minus wl squared over 4 EI times x squared. And that's it. That's our solution for v as a function of x. The last part of the problem was to evaluate at x equals L. So I will simply take my solution and plug in v of L equals negative w times L to the fourth over 24 EI plus wl times L cubed over 6 EI minus wl squared times L squared over 4 EI. To reduce this, I'll factor out all the symbolic terms. I have a wl to the fourth in every single term over EI. In fact, this is a good check to make sure my units are right, that all terms have the same dimensions, and in this case they do. Now the numbers from the first one, negative 1 over 24 plus 1 over 6 minus 1 over 4. Now what we need to do is find the least common multiple, which is 24, since 6 and 4 both go into 24. We multiply the second term by 4 over 4. We multiply the third term by 6 over 6. A little bit of math to reduce. I have negative 1 plus 4 minus 6 over 24, which reduces to negative 3 over 24, which reduces to negative 1 over 8. So to summarize, v of L equals negative WL to the fourth over 8EI. This is a general solution for any cantilever beam with a uniform load W. We could apply it with a variety of numbers to actually get a value for the deflection. Notice that it's negative, which tells us that our deflection is going downward, and we expect that for the loading on this beam. So that completes this example.